website at Hot Stamping. And one of the reasons why I volunteered to do this topic is that I have to start doing bigger training classes myself on delivering training classes on hot stamping. So I wanted a little bit more practice and familiarity with the content and materials. So I don't profess to be an expert at hot stamping any more so than I am a normal self-proclaimed die expert. So this is what I know and have learned about hot stamping recently. If there's something that you guys know or want to share with me, please feel free to chime in at any time. All right. When it comes to hot forming and hot stamping, one of the first things that we could talk about is why do we do it. One of the big things is that we have the of course the safety standards that we're trying to achieve. We want to make our cars safer, our vehicles safer for the passengers. So in these two pictures right here, you can see in these two examples of one of them is a front impact with an offset, the other one's a direct front impact, and you can see really significant incursion into the passenger compartment. So these would have been very potentially deadly and certainly injurious car accidents. However, if you look at this picture at the top, you can see that that front door barely looks like it's got any damage at all. Very little intrusion into the passenger compartment. And that's one of the big pressures behind using hot forming technology. And one of the reasons why we're using more and more hot forming technology is we're trying to deal with the seeming contradiction that we have between the fact that we want to make all of the cars lighter in order to reduce our CO2 emissions and drive down or increase the fuel economy and reduce our CO2 output. Right? So that certainly does make making the cars lighter more important. But of course, we do have the fact that our vehicles are getting more and more complex. The shape of the vehicles, the content of the vehicles, the safety that we're trying to achieve are all increasing the complexity of the types of parts that we have been making and will be asked to make in the future. So hot forming is really something we're trying to do to address that contradiction of how do I make it lighter, but of course make it stronger and have more function, right? And we're using this new material of boron hot stamping steel to address that. Right? So in order to resolve that contradiction, we are using increased lightweight alloys. We are seeing, people going back to aluminum for the Ford F-150 is the all aluminum truck body. That was done to maintain the strength and stiffness integrity that Ford wanted in their F-150 while still making a lighter vehicle and safe vehicle in order to get better fuel economy. So that all aluminum body of the F-150 and frame was certainly an attempt to go for lightweight alloys. However, one of the problems with aluminum is that aluminum is still very CO2 intensive, and that means that overall, if you start making a high aluminum fleet, you'll still overall have a relatively large CO2 footprint. And that's one of the reasons and one of the things behind this increased use of high strength, ultra high strength, and advanced high strength steels is to ensure that we're getting strong lightweight vehicles that are safe and offer great integrity, however do not necessarily increase the CO2 footprint of that particular vehicle. Right? So this is one way that we're trying to do it, is material with better strength at a reduced thickness. However, this does have a kind of a double impact on our ability to deform the material. As you go to stronger materials have the tendency to resist the desirable deformation that we're trying to apply when we're sheet metal stamping or stretch forming that material, right? Because the whole reason we wanted to buy the high strength material is so that it resists the undesirable deformation in that front impact or that offset frontal impact. However, it's going to also mean that that material is going to inherently want to avoid the deformation that we might be trying to apply in a sheet metal stamping die. Right? And you can't necessarily have it both ways. Can you have a material that resists undesirable deformation but accepts what we think of as desirable deformation? And generally, I have to say, well, no, the material cannot tell the difference between what is desirable deformation and undesirable deformation. Hot forming and hot stamping is a way around that, because that is using temperature and heating that material up is a way that we're differentiating the desirable deformation that we're doing in the hot stamping operation from the undesirable deformation, which would be the deformation in ambient temperature of a vehicle in crash. Other challenges raised by trying to go to these advanced high-strength materials and increased strength materials, not only are stronger materials typically more difficult to form, right? They have lower forming limits or formability limits, but they also tend to have greater amounts of spring back. Right? So as we've tried to introduce these lightweight vehicle construction, whether it's high-strength steel or whether it's aluminum, is that in both high-strength steel and aluminum we do see a greater amount of overall spring back. And that makes it very difficult for us to achieve our dimensional accuracy goals, our PPAP goals. Right? It doesn't matter if I can make the part, if I can't make it dimensionally accurate to the right size and shape and tolerance, that new strong component or lightweight component doesn't do me any good. So these are the challenges that we're using hot stamping and hot forming to try to address. When we talk about hot forming and hot stamping these materials, we're usually talking about one very specific type of material that you might call boron steel. And I've also seen that steel called out with a numerical designation. Let me make sure I get this right. 22 MnB5. That would be this boron steel material whose chemical composition I have in this little table at the bottom of this slide. Right? So boron steel is a high carbon steel. It's got a significant amount more carbon than would a typical stamping steel. When we think about mild steel and a draw quality, we're usually talking about material that has a carbon by weight percentage at 0.08 or below. Right? If you ever hear people talk about steel, and maybe they've talked about steel in terms of the SAE designation, 1008 steel or 1010 steel. When you talk about 1008 steel, that 08 represents the maximum allowable carbon by weight in that material. So when we look at this hot forming steel, we're talking about steel with 4 times as much carbon, at least, more than your typical mild steel. Significant other things that you'll see is that there's a significant amount of manganese, right? That's Mn. The element manganese, we're seeing 1% of that material weight of the Mn. That's why we're calling it out in that material name. And there is this trace amount of boron. And this trace amount of boron really does have a profound effect on this material's behavior. And what happens with this material is that when this material comes from the mill, its non-hardened strength characteristic puts it in this range on the sheet steel, what people call the banana chart, that it has a range of available strengths at room temperature from the mill somewhere between 500 and 750 megapascals in strength. That'd be somewhere around 35 to 50 ksi tensile strength at room temperature without this hardening. Then what happens is that you actually, and you can see that It's strong material, but it has a relatively low amount of overall elongation. That this material, while it has a very high strength, you might be lucky if you could deform it 10 to 15% before it fractured and failed. So these are materials that have relatively low amounts of natural ductility, natural deformability. However, when you heat these materials to 900 degrees Celsius, what happens is that material now becomes highly deformable, and it deforms quite well at these high temperatures, and now you can see 50 to 60% elongation of that material inside of the tool. And that's pretty good. That means that we can form even more complex shapes than we normally would use interstitial free or extra deep draw quality to form without causing a fracture or a failure in the material. But what's really cool about this idea of hot forming these specific grades of boron steels is that when you cool and quench that material, the material ends up in many cases significantly stronger than it was even coming out of the mill. Now that's not true for every other grade of steel that you might think of, right? You can't do this trick of hot forming the material with plain 1008 1010 steel. If you take 1008 1010 steel and heat it up to 900 degrees Celsius and then form it and then cool it, that material is going to come back to you in an annealed state, a softened state, and that material is going to be less strong and less structurally sound than it was when it came off of the cold rolling mill. That material would have very much a hot rolled quality to it, and it would lose a lot of the strength and characteristics that we like in our mild steels. However, this boron steel, when you heat it and cool it in this manner, you can end up with a material that is up to 50% stronger than the material was when we bought it from the mill. So we're adding value to the material in two different ways when we're doing this hot stamping. We're adding value by making it take on a new shape, and we're adding value by making the material stronger than it was when we first bought it. So that's a double dip as far as value add manufacturing processes. It's stronger and it's in the product shape. So what we see is for these materials, again, very much a similar chart that we had just on the previous illustration. But what's interesting about this one is this illustration provided by Audi showing the content that we have of the high-strength steel inside of this A3 vehicle model. You can see that we're using regular mild steel for components like the cowl, the wheelhouse, the body in white parts of the panel that are not vehicle that are not structural. However, these engine compartments are using this high strength advanced high strength materials, and we can see hot forming materials in the A pillar, in the B pillar, in the impact beam across the width of the car, in the firewall. All of these areas where we want this very high amount of strength to make sure that the passenger compartment is not having intrusion during an impact, we can see people using these high strength steels. Now this is all because of the metallurgical effect of, some people might call this the nose diagram, but this is the time temperature characteristics of these high carbon boron steels. And what happens is that when you heat the material up to this higher temperature and then allow it to cool, if you let the material cool slowly, the material is going to form a certain kind of microstructure, whether it's ferrite or pearlite or austenite. Right? These are the microstructures of common carbon steels. However, if we take that material up to temperature and we're able to quench it in a rapid enough sequence, we're able to bring that material into a characteristic that we call martensite. And martensite is a microstructure common to these high carbon materials that is much stronger and has higher strength than we would expect in a mild steel that was a ferritic or austenitic microstructure. So it's very desirable with this hot forming to heat the material up to this wonderful temperature around 900 degrees and then cool it and quench it pretty rapidly in order to force this martensite microstructure to form in the material without seeing the microstructure pass through different phases or different types of microstructure. And that's the reason and that's the benefit for using these hot stamped, hot forming boron materials. So when we think about hot forming, there's two different ways you can think of these hot forming materials. Another term for hot forming would be this term that we call press hardening. Right, so same thing. If you hear people talk about press hardened materials, die hardened materials, they're talking about the same thing that I am right now. They're taking a blank of material, they're heating it up, forming it, and during that forming operation, quenching it to this martensitic microstructure, martensitic phase of material. There's two schools of thought when you think about this hot stamping. There's what we call direct hot forming, and there's indirect hot forming. Direct hot forming starts by taking the coil of material, unrolling it, creating your blank, taking that flat blank and passing it through a furnace to heat it up very uniformly to a temperature around 950 degrees Celsius, loading it into the stamping die, and inside of the die not only deforming the material, but as we're deforming it, also cool it and quench it down to ambient temperature, right? Something in the ballpark of 200 to 80 degrees C, right? When you get this material down into the range of 200 degrees C to 80 degrees C, you've already cooled it sufficiently that it's going to have the appropriate microstructure. Then potentially you could use a robot to gingerly unload that blank, let it go down to the conveyor belt so that it can get racked, or bring it to another station for laser cutting, laser trimming. Right? This is what we would call direct press hardening or direct hot forming. Indirect hot forming starts off with the same operation, but instead of going directly from the blanking operation into the furnace, you can actually form that material some of the way, partially, at room temperature. That's going to allow you to make a slightly deeper part without necessarily having a high degree of localized thinning. Right? One of the problems with forming these materials at such high temperatures when we do this direct hot forming is the fact that any thinning that does happen tends to be highly localized. Right? The material is heated up and it's very ductile at that point. And what will happen is that the thinning can get localized maybe in ways that are slightly undesirable. If we do the preforming at ambient temperature initially, that allows us to do a little bit of initial stretching of the material and hopefully be able to maintain a relative uniformity or at least less localized thinning behavior. Then we can put it through the furnace. So take the preformed thing and now heat it up in those furnaces to 950 degrees C. Then stamp it even more in this temperature controlled die in order to quench it, and then go to the laser cutting. And that would be indirect hot forming. So we can see that a variety of manufacturers. Here's a picture provided by Volkswagen for the Volkswagen Passat. Their use of press hardened materials on their most recent Volkswagen Passat allowed them to reduce, on average, most of their sheet metal thicknesses of these parts that are highlighted in red have each been reduced by about 0.2 millimeters in thickness. And that meant also that we could reduce the overall number of parts. They're able to take what used to be a stamping plus a reinforcement and replace that two different stampings, two different parts in the assembly, with a single stamping that is press hardened. That reduced the overall number of forming operations and therefore reduces the amount of tooling. And if you reduce the amount of tools, then presumably you are driving down in one aspect the manufacturing cost. They were able to do this and in the meantime achieve an increase in overall part stiffness, because now if we have fewer number of parts in our assembly, the assembly is more integral and therefore stiffer. And of course an overall stronger component, because we've achieved a stronger component while reducing its mass. And that has very positive effects on passenger and vehicle safety. All right, so here are some other parts that were used. Again, that was the Volkswagen Passat, but there are components that you might see people hot stamping. Here is the tunnel. It used to be a single component with 2 reinforcements on the outer, 2 reinforcements inside, which is now a single stamping. 5 kilograms, that's a 10-pound reduction in the assembly. And we've seen in this example a B-pillar. The B-pillar used to be the B-pillar itself, a B-pillar inner, a B-pillar reinforcement, and then reinforcements for the pillar, the hinge, and the latch areas. And of course by reducing those to just 2 hot formed components, we saw also there 4 kilogram reduction in overall vehicle mass. Similarly, door sills, roof panels and roof bows, B-pillars, tunnels, the firewall base mount and the subplate at the front of the passenger compartment, all candidates for this hot stamping. So we are seeing an increased amount of content in our vehicles